Welcome back. This lecture will be a little bit different from the previous lectures in that I've already written out all the notes. Unfortunately, while I was recording and writing this out for the first time through the lecture, it somehow stopped recording. So we'll do it again with the notes here. Maybe we'll find that this is a better way to go. It's a little bit quicker. I still prefer writing them out as I go. So we're going to talk about today the lapped orthogonal transform. The lapped orthogonal transform, abbreviated LOT, L-O-T, is also called the modified discrete cosine transform, and you'll often see it referred to in that way. Now, the modified discrete cosine transform is used and was developed primarily for audio applications such as the MP3 coder, and it was developed because of the problem that we mentioned previously with block transforms. So if you take a transform that can reconstruct a function on 0, 1, use it to reconstruct that, and then use the same transform method to reconstruct a signal on 1, 2, and 2, 3, and so on and so forth, everything will work out fine. You actually get a perfect reconstruction or representation of the signal on L2 over the whole real line. But the problem comes up if you ever perturb any of the transform coefficients. And this might happen if, for example, you quantize coefficients like we did with JPEG. The result is that the signals won't line up perfectly at the boundaries. And you can hear this. It sounds like clicks or buzz, depending on how big your blocks are, if it's a sound. And if it's an image, you can see the grid pattern, and they call it blocking in images. So if you see these little blocks show up in an image, it's because of this boundary discontinuity. So the lapped orthogonal transform smoothly interpolates between blocks. And the way it does it is it uses the cosine 4 transform that we've discussed previously, and it uses a window. So let's talk about this window. It's very important. So the window, which you call G of t, is this shape that is perfectly flat on the top between 1/4 and 3/4. It's equal to 1. It's 0 outside the range, minus 0.25 and 1.25. And then in between, it monotonically increases, and it has some properties. These properties are over on the left. Okay, so the first property that we've listed here on the left, that it's equal to 0 outside that range you've already discussed. The second one is that it's equal to 1 between 1/4 and 3/4. The third is that it's symmetric about 1.5. So we have this nice symmetry. The fourth is that it monotonically increases between 1/4 or minus 1/4 and positive 1/4, and because it's symmetric, then it's monotonically decreasing between 3/4 and 1.25. And then the final property, very important, is that if you square the window and add it up with a shifted version of itself, it adds up to 1. So over here on the right, we can see our window in blue. Of course, once I highlight it, it tends to look black, so I'll get rid of the highlighting. And we have a shifted version by 1 in red, and they overlap, of course, between 3/4 and 1.25. If we square both of those windows and add them up, over that overlapping region, they'll add to 1. And of course, if we square the window right here at the top, it already equals 1, so squaring it, it'll still be 1. And the result is that these windows have a value, when we sum up all shifts of the windows, all integer shifts of the windows, and square and sum them up, they equal 1 for all t. So that's an important property. Okay, let's now that we have this window, let's see what we can do with it. So, by the way, there are a lot of windows that would satisfy this. The particular one shown is often used, and it has what I regard as a rather strange looking function. Shown here in gray, it's the monotonically increasing and respectively decreasing portions are the sine of a sine squared function of t. So it's kind of a strange function, but you can square that and sum them up, and you find that yes, indeed, you do get these nice properties. Okay, so once we've done that, we can define our basis functions as a product of our window and the cosine 4 transform. So cosine 4 transform basis, so you don't have to scoot back and look for it, is given right here in orange or green, and g of t is given by those properties above. So this is our transform. I'll bring up a plot of what this looks like for this particular g window function that we've chosen and the cosine 4 transform in just a moment. Okay, so the LOT basis functions look like this. We have they tend to have a sinusoidal shape, but you can see the effect of the window, how they taper down to 0, and the first ones have a little bit of a strange shape, but it really becomes clear as you get to the higher frequency ones. And you can see you have a pretty high frequency, but it tapers down to 0 at the edges. So this is the basis for the LOT transform. So if we well, let's see. Let me give an example first, and then we'll look into exactly how this works, because it's a little bit strange. Okay, so here's an example of a signal x of t, and the corresponding LOT for this particular signal. Well, first we show a zoomed version, and then we show the transform coefficients. Here green represents 0, and we have positive and negative here with red and blue coefficients used to represent that. So we have a localized frequency transform. You can see the time for which it occurs, this pulse, and we can see the frequency at which that pulse is concentrated. So going forward, I'm going to go through the next 4 pages of notes rather quickly, and I can't believe I'm saying this as a professor. You might think that everything we teach you we regard as very important, and all of this is important to some degree, but it's not as important to me that you are able to, say, derive the LOT as it is for you to basically understand some of the concepts that go in here, and that you're exposed to a tool that's very useful in audio processing and in other block transform situations. So I've already written out the notes so that we can go a little bit more quickly through things. So first off, we want to show that our new LOT basis, these phi functions, can be used to represent any function x of t as shown. So, in other words, are they an orthonormal basis, phi nk of t for L2 over all of R? So we've already shown that we can do this for the cosine 4 basis functions. So that was our psi nk of t, but we haven't shown that yet for phi. And phi has this weird property that it's not defined just on the interval from 0 to 1, but it extends beyond that. So first, we're going to write down the projection that yields us our coefficients, our transform coefficients. And that's shown right here. So this will be equal to our alpha n comma k. And we've done nothing other than write it down according to the definition that we have, where we have, of course, our phi n comma k of t expanded out in that manner. Okay, remember that psi k of t in general is the cosine 4 basis, and although the function itself can be evaluated at any point in t that you might like, as a basis it was defined from 0 to 1, but now we've extended it to be from -1/4 to 5/4, and that essentially is done by multiplying by this window, multiplying the function by the window, and so since the window is 0 outside that interval, the result is only defined on that interval. So we're now defined from our psi k of t, we're looking at an extended range. Okay, psi k of t for our cosine 4 basis had some nice properties. It was symmetric about the origin, and it was antisymmetric, or odd. It was an odd function about t equals 1 and t equals -1. And so that's represented here. That's supposed to be a 2. So a property that we're going to take advantage of in the next little bit. Okay, so here we are. We have our projection that we're looking at, and we're going to divide this into 3 regions. The first region will be the rising edge of our window, so that's -1/4 to 1/4. The next region will be the flat part. It's from 1/4 to 3/4. And the final region will be the decaying part, and that's 3/4 to 5/4. Well, we've already done some analysis of this middle part, at least that particular function, not necessarily on that interval. But let's go ahead right now and start by looking at this first part here, circled in red. From -1/4 to 1/4, we're going to divide that again now into 2 regions, from -1/4 to 0. And one of the reasons this is all written out ahead of time is because it's just some math. I don't know. You can look at it, perhaps just look at the slides later at a slower rate if you want to dive down into it. But nothing miraculous here. We're just dividing this area up. But the reason we're doing this is because we happen to know some of the properties of yk of t. One of the things we know is that it is an even function. It was defined that way. So because of the even nature of this, we can now recombine these two sums. The first one we have xk of t, or I'm sorry, x of t times g of t times yk of t, and we're looking at 0 to 1/4. And so that shows up here, x of t, g of t, yk of t. Now for the second one, we can put in a negative t. And so now we would get x of negative t, g of negative t. But since y, or psi rather, is even, that's just psi of t. So we can factor that out. And now we have the same interval, namely 0 to 1/4. This is good. The more we can do to get things into the 0 to 1 interval that we are comfortable dealing, perhaps the easier things will get. Now we can repeat this for the last term, and we get, applying similar things, we get an expression much like that, except that now instead of x of negative t and g of negative t, we have x of 2 minus t and g of 2 minus t. And we're once again inside the 0-1 interval, in this case from 3/4 to 1. Okay, so let's look at all these equations. We have this expression number 1 that came from our leftmost expression over there. We have expression number 2 that we haven't done anything with. And then we have expression number 3, which came from the last term, corresponding to the falling edge of the window. When we combine all of those, we're going to get that x of t projected onto phi 0, so lag of 0, comma k of t is equal to 0 to 1. And now we have just this function z. Well, as you might imagine, this function z is going to be a big expression. But everything in 1, 2, and 3 were multiplied by psi k of t. So we have our psi k of t right here. And our z is going to be this strange function between 0 and 1/4. It comes from expression number 1 right here. And from 1/4 to 3/4, we have an x of t that came from expression number 2 above. And likewise from expression number 3, we have an expression from 3/4 up to 1. Okay, well, since our psi k of t we already know is form an orthobasis for 0, 1, then for that frame we know that it forms an orthobasis, you know, it can represent z naught of t. So let's look at what this looks like then. On the left we have the expression that we're trying to evaluate, which is x projected onto phi, in this case 0, comma k, times 0, comma k. So we don't have the time intervals taken care of yet, but we'll do that in a minute. And we've just shown that that's equal to z projected onto psi. So z is our new strange function that has x multiplied by our window, and psi, of course, is our cosine 4 basis. And we just use the regular projection on L201. So that's a different projection than we have over here. And we still have our phi 0 comma kt, which over on the right is now going to be g of t times psi k of t. Where to go next? We've got a lot to unpack still, so let's keep looking at this. Okay, so we can factor out the g of t. It's not a function of k, so that factors out front. And then on the inside, we have this what we've seen as a regular old kind of building up a function from using basis functions, except that things are a little bit different here. We have our coefficients there. Our psi is actually defined on -2 to 2 instead of our usual 0 to 1. So the coefficients, which are projection onto 0, 1, don't quite match yet, but we'll worry about that in just a minute. And we have our g out front, which is non-zero only on -1/4 to 5/4. Okay. Well, what do we have? We do know, although it's going to be doing some things outside this interval, based on the fact that psi k of t on the interval 0, 1 is an orthobasis, we can state that this large expression is just going to be equal to g of t, because the g comes down from out front, times z naught of t for t between 0 and 1. So this is true. It equals that on that interval, but the sum reproduces a z naught of t on the entire interval -1/4 to 5/4, because we're actually multiplying by something that's defined on a larger interval. Okay. So what we have here, and this is important, is that we've reconstructed g of t times z naught of t for the interval 0, 1, but we can extend the synthesis interval to -1/4 to 5/4. Now we repeat the whole operation for n equals 1, because that first one was at a lag of 0 time. So now we're going to do a lag of 1 unit of time. And our z is going to be almost the same, except the only difference is that our g's have now moved. Okay? And we're evaluating this over a different interval. Those are the differences. And of course we have the symmetry that shows up in a different spot. And we can do the same for g, or for n equals -1. And so now we've come up with our 3 parts. And I've already color coded this. So x of t, that middle part, defines this part in the middle. And the green part corresponds to that overlapping region. So when we add together all of these terms, we have we've been able to reproduce z negative 1 t times g of t plus 1, z0 of t times g of t, and z1 of t times gt minus 1. Is that equal to x of t for this region right here? Between minus 3/4 and plus 1 3/4? That's the big question. So let's multiply everything out. Since we're multiplying g times z, and z itself has g's in it, when we plug this all in, we're going to get, as highlighted in blue down here, some g squared functions. And so our two blue ones are both multiplying x of t. When we sum that up, the sum of the windows is equal, or squared, is equal to 1. So that gives us just x of t. These two terms right here, x of t. Now we have this minus x of minus t and plus x of minus t multiplied by this g1 minus t and gt plus 1 and g of t and g of minus t. Well, g of t is equal to g of 1 minus t. We already know that. That was part of the definition, so that's just g of t. And g of t plus 1 is equal to g of minus t. That was also in the properties of g. So here, we're essentially canceling out those terms. And so we get, at least over this interval, when we sum up g of t plus 1 times z of minus t, z minus 1 of t, and g of t times z naught of t, we get just x of t. So choosing the properties of those windows, as you can see, was not an accident. And this will hold true for every overlapping region. Well, we already know we can reconstruct the yellow highlighted areas there, and now we've shown that we can reconstruct the overlapping areas. Therefore, we have this LOT basis can actually be used to reconstruct a signal. It's very, very strange that we have these overlapping things, but here's the beauty of it. Since the basis functions always ramp down to 0, if you're doing some approximation, say you are quantizing coefficients, at the boundaries it will always ramp down to 0, so you're going to have a smooth transition between blocks. And it's all in the properties. Okay, so there's a lot to wrap our heads around here. Just a lot of fancy little math, and we proved that everything works. So what exactly is going on when we do all of this? Well, if we go back to looking at the basic picture of our overlapping windows, what we're finding is we've defined these in a very careful way so that we have an ortho basis such that one window ramps down where the other window is ramping up, and we still maintain orthogonality in this nice ortho basis. I've tried to think of a good way to explain it, and it just is kind of hard to do because, in essence, the way this is defined, it's just defined to work out perfectly, but it's a little bit hard to visualize. But one last look here at the basis functions. We can see here where we have something like this is overlapping with maybe another function right here. These are chosen just perfectly so that even though these only overlap for a little region, that region, when we take those product and we sum it all up, it still adds exactly to 0. And so we have this, when we have shifted neighboring windows that overlap, they still maintain their orthogonality to each other. So that's the lap orthogonal transform. It's kind of a long lecture, and I apologize for that. We covered a lot of material. And I'm not going to hold you responsible for the theory of how it all works, but you should remember that such a transform exists, and that here we have a block transform that we can reconstruct a signal on the entire line, and it's also robust to perturbations in the transform coefficients. Thank you.